Hi, I'm David. I'm looking at the screen now with my video because people complained, a lot of them have never seen my face. Hello, I'm David, I'm coordinator of the Maths Learning Centre. Now you've seen me if you've never seen me before. Okay, cool. Alright, this is a revision seminar for Eng Maths IIB. So if you're listening online and that's not what you expected, then go and find the right one. And I said I would do something on complex calculus. Yes, and if you're interested in vector calculus, there's already one from last year on the Eng Maths IIB page of the Maths Learning Centre's website. Right, so do beware, making this up. And I've gotten someone's lecture notes from this year to just have a quick flick through what's going on with it. And I will do my best to try and draw it together so that it makes a bit more sense. Though people have said to me that, you know, I come and sit next to them near the Maths Learning Centre and they go, wow, that makes so much sense. And I go, that's great, thanks. Sometimes it doesn't give me faith in what the lecturers are doing if I can make it make sense with such little effort. So, yes. Okay, so I'm just going to write that down. I really shouldn't be recording statements like that. That's so bad for me to say that sort of thing. Okay. So, so far, let's see if I've got this right in Eng Maths IIB, there's like Laplace transforms, which required you to remember how partial fractions work from the dim dark ages of Maths 1A, and then there was vector calculus, which had all these theorems named after various people, one of whom happened to be your lecturers, but it's not your actual lecturer, of course. And then there's this complex calculus bit, which sort of feels in a lot of ways like the vector calculus, but in a lot of other ways it's not. And I'm just going to start by sort of having a quick look at some stuff that comes before this that's really useful to know. So, partly because even if you know it, it'd be really great if next year's students could use this as a way of studying this near the beginning of the course. So the idea is you've got these complex numbers, you've got your various families of number, there's the natural numbers, and they're contained in the integers, and they're contained in the rational numbers, and they're contained in the real numbers, and then they're contained in the complex numbers, and this is like the awesomeness that is the complex numbers that we're living now. And the complex numbers are really cool because they're algebraically closed, which means that you can do any polynomial and all the solutions of the polynomial must be in the complex numbers, which isn't true in any of the other number families. And so from an algebra perspective, which is where I live, it's just awesome, the closedness of it. And you know, there's no such thing as elliptic quadric with the complex numbers because everything factorizes. It's, yay, everything's hyperbolic, and I love the complex numbers. And complex numbers were invented in, you know, roughly around the same time as Alice in Wonderland was written. And if you read Alice in Wonderland, you can find some cool stuff in there about the complex numbers that's hidden in the stories. So there you go. That's got nothing to do with your course, but that's why I love them so much. And the idea is that you can make them this way. You get a real number, and you do that. That's a complex number. And these are both real numbers. And I is a solution to I squared is minus 1. And they call this number here the real part. And this number here without the I, the imaginary part. It's really important not to include the I. It stuffs up all your calculations if you include the I. And it's traditional to call them Z for no good reason, mainly because we've already got X and Y, and so we choose the next letter Z. And the classic thing about complex numbers, which makes them so useful for vector calculus sort of stuff, is that every complex number has a representation as a point on 2D space. So you would have this, and this would be A, and this would be b, and that dot there is the complex number a plus bi. Right, as far as I'm aware, this is called an Argand diagram. Okay, so far we've got two representations of a complex number. We have complex number as a plus bi, and complex number as a dot on the real plane. And there is a third representation of complex numbers, and I'm going to just draw this out in a second. There's a third representation of complex numbers, which goes, you could also represent your complex number as r e to the I theta, like that. Also known as, if you did it at school, cis theta, where cis is short for cos theta plus I sine theta. So cos I sine, right? But most useful for complex calculus is this version. This is called polar form. I'm just going to draw a little table in a second. So there are three main representations of complex numbers. The middle one is the bridge between the other two, because in the middle one, if I just do it in a different colour, actually I'll do it here. What you do is you go, that distance is r and the angle is theta. Okay, so that's your representations of complex numbers. And I should point out, real numbers can be represented as dots on a line. Okay, every dot on the line has a number, the number in the middle is 0, and every other number is a number of its own, and you can represent complex numbers with lengths. So real numbers with lengths. Complex numbers are dots on a plane. So they need two coordinates to tell you where they are. And one of the purposes of complex numbers is to create a way of representing points so that you can multiply the points together. So with vectors, we can add points together. You just add the coordinates and it works great, or you treat them as arrows. But with vectors, you can add points, but with complex numbers, we have a way of multiplying points. And that's really useful if you want to represent something with geometry using raw numbers. Every number in that plane has, every point in that plane has a number of its own. Okay, so we don't treat this as two coordinates, as coordinate A and coordinate B. What we're trying to achieve is a Zen-like state where we say, actually, the whole thing is one number. It's just A plus BI, and it's a number in its own right. Okay, there you go. There's a bit of maths philosophy for you. So, just let me just summarise that. So you've got what they call the Cartesian form, which is your A plus BI. And you've got your polar form, which is your r e to the I theta. And then there's your graph, or graph if you like, which has both. You know, it lines up with A and B, and that's the r, and that's the theta there. Okay, cool. All right. That's great. And the reason that we have the different forms is because they're useful for different purposes. The A plus BI is awesome for addition and subtraction. And your polar form is good for times and divide and powers. That's what we're looking at there. Cool. Right, I'm just going to skip most of the rest of that. Yeah. So, just some rules. We're going to treat it the same as algebra, and the algebra works the same way that algebra works in everything else. And the reason we write our polar form this way is so we don't have to remember special rules. Powers work the way powers ought to work. Okay? So, A plus BI plus C plus DI is just A plus C plus B plus DI. You know, it's just algebra. Okay? Nothing special. And so addition's really awesome for that. Multiplication, you'd expand the brackets. You know, AC plus ADI plus BCI plus BDI squared. But I squared is really minus 1. Okay, and that's pretty much it in terms of the deal. The interesting thing about this is the AC minus BD is the determinant of a matrix. Yeah. No, it's not. Ignore that. The AD plus BC is. Okay, so that's classic. It's just algebra, and anytime you see an I squared, you can replace it with a minus 1, and you should replace it with a minus 1, and then you can simplify it down. And that joke goes for all situations, anywhere where you see an I squared, always comes out to minus 1, and that's the real property of I squared. Multiplication's great, powers are just crap, and so we do in the other form to do powers. Okay, the other form, division's awful too. I'm going to do it with an alpha and a beta because it's easier than writing theta and phi. So that really is the number r, the real number r, times the number e to the I theta, and you can multiply them together. So you're going to get the r times the s, and e to the I alpha plus I beta, because when you multiply powers they add together, right? Power times down the bottom is plus at the top, and that's why we write it as a powers, because then we don't have to remember special rules for what happens to sis's. So in essence you times this R part and you add the angle part. And it works the same for division, and powers is the way that powers work. So the number here, real number part gets powered and the angle gets multiplied. Okay, that's the deal. It does what it's supposed to do, and that's the reason that beyond high school, it's the reason we write our things as powers, because then we don't have to remember special rules because it works the same as the way powers work. That's the deal with complex numbers. But there are two things else that is worth pointing out. Is that the functions that you can do on these complex numbers, it's a specific function called the modulus. So the modulus is the length of the complex number if you imagine it as an arrow. So I always call it length, but its official name is modulus. And the length of a plus bi, we use Pythagoras' theorem. And it is literally the length as drawn on that picture that I drew before. So this picture here, that length right there, that's the length. And the length of r e to the I theta is r. And it's literally length as the way vectors work. Okay? And so that's why I will start calling this r the length. It's r for radius, but it's just how far away that complex number is from the origin. And it is worth pointing out that without the r, the length of e to the I theta is 1. Like that number all on its own without the r, its length is 1. So all of the complex numbers of length 1 are e to the I theta for some theta. Okay, cool. It's modulus. And it's good to know what modulus does to the other operations. The length of complex number times other complex number, it expands out over time, over multiplication. And it also expands out over powers. So anytime you learn a new function, you should try and figure out what it does to all the things you know. That's what it does. It expands out over division too. That's cool. All right. See if I've got everything on my pages here. Cool. And then there's a thing called the argument. Which is the angle. So when we do our RE to the I theta, that's the argument there, the angle. Right. Now, the problem is that argument, there is not one single angle that produces that same complex number, because you could go around any number of times and end up in the same spot. So every complex number has infinitely many possible arguments that are all 2 pi apart. And it is completely not correct, it's not correct to say that if you have a plus bi, that the argument of a plus bi is tan inverse b over a. That is in fact not true. It is only true if your complex number is in the first and fourth quadrants. If it's not in the first and fourth quadrants, that will in fact be wrong. So it's worth not doing that. Okay. If you have a plus bi and it happens to be equal to re to the I theta, then tan theta is totally definitely b on a, but theta might not be arctan of b on a, because tan inverse only produces angles between minus pi on 2 and plus pi on 2, and your angle might need to be bigger. So what you do need to do when you're finding arguments is to just locate your angle, your complex number. So as an example, if z is minus 1 plus I, that complex number is over here, minus 1 plus I, it's just there. That's where z is. And if I do the tan, if I draw a little triangle here with a theta in there, then tan theta is 1 over 1, which is 1. And in fact, it will be minus 1 because it will be minus 1 over minus 1, right? It will be minus 1, which would tell me that theta is in fact, if I ask my calculator, theta would be minus pi on 4. And if I actually use the angle of theta as minus pi on 4, I would start here and go minus pi on 4, and I would end up here. And that is not where my complex number is. My complex number is over there. So in fact, my theta that I need is actually pi minus pi on 4. So in fact, the argument of z is in fact pi minus pi on 4. So it's 3 pi on 4. This might not actually come up in your course, I don't know. But it's worth mentioning that there are 2 angles between 0 and 360 degrees that produce tan is minus 1, and only one of them is your complex number. So even though your lecture notes actually say theta is tan inverse of y on z, that's not y on x, that's not actually true unless your complex number is in this right-hand side. So on the left-hand side, you're going to have to adjust it by about pi. Okay? But any multiple of pi on 2 from there will produce the same complex number, because I could go round like this, round another 2 pi and get to the same spot, and round another 2 pi and get to the same spot, and back 5 2 pi's and get to the same spot. So there are any number of possible solutions to what angle produces that complex number. The length will be the length is root 2, but the angle changes. So the principal argument they call is the one that fits between minus pi on 2 and plus pi on 2. So the smallest sized angle that produces your complex number is called the principal argument. So this is in fact the principal argument, because it's the smallest sized angle that produces my complex number. Okay, so back here, I'm just going to add it to here. If theta is between minus pi and pi, then it's the principal argument. Where principal is spelt like principal of a school because it means first or most important argument, as opposed to principal with an LE, which would mean a rule. Okay, there you go. So they're the main bits of information about a complex number. So let's just think this through. Bits of information about the complex number was the real bit, the imaginary bit, the length, and the argument. And also you can write it in different forms, and you can do addition and multiplication. That's all great. Okay. And finally, there is one more thing that you can do to a complex number that is worth knowing, and that is you can conjugate it. So if you ever studied another language, you know that you conjugate verbs, which means that you change them depending on whether it's the past tense or whether it's who's doing them. It's not like that at all. And if you know what conjugate means in other senses, you might think there's some sort of horrifying thing that they do to produce new complex numbers by interacting with each other in a carnal sense. It's not that either. Think about that for a bit. Go look up the other meanings of conjugate, because that would be conjugate. So if you have a complex number that looks like this, then its conjugate looks like this. Of course, if it was minus bi first, it would become a plus bi. And or in polar form, that looks like this. You minus the angle. And why do we care about conjugates? Well, there's two reasons. One is that a number times its conjugate is a real number, which is the square of the length of the number. So it's a bit like dot products, right? So when you do, with vectors, if you dot a vector with itself, you get the square of the length. Well, this is the closest we can get for complex numbers. Instead of dotting it with itself, you dot it with its conjugate to get the square of the length. It's also, the conjugate is also the only function that will produce, number. If you've got a complex number, the conjugate is the only number that you can both add to and multiply by your complex number to get a real answer. So z plus z conjugate is real, and z times z conjugate is real. So conjugation is the only thing that you can do to complex numbers so that those things are always true. That's really special as a thing that you can do to complex numbers. So those are some facts about conjugates. Okay. That's just really cool. It's also an automorphism of the complex numbers as a field. It's cool, right? And it's also one of the few things that expands out over both plus and times. So we also have that the conjugate expands out over conjugate. The conjugate expands out over plus, and the conjugate expands out over times as well. Which is not something that most things do. So if you go back to Maths 1 anything, you will have come up several times with Maths Learning Centre staff members saying, you can't expand out square root over plus, what the hell are you doing? Nothing expands out over plus except times. Well, that's wrong. With complex numbers, conjugate expands out over plus as well. Conjugate expands out over everything. It's awesome. Okay, it's fabulous. That's why it's called an automorphism. But if you never study study algebra, then that word will be meaningless to you, but it's a great word to know, right? It's a cool sounding word. So anyway, that's why I love the conjugate, because it's an algebra thing. But it's important mainly because of this. Okay, but it's also the only thing that you can do to complex numbers that will expand out over plus n times and produce real answers at both times. Right, that's your whirlwind tour of what complex numbers do. That clock doesn't tell me anything. Right. And then, now we're up to the cool stuff, but there's some stuff that we need to talk about first before we get to that. So we're going to go rewind and go back to Maths 1B, and we're going to talk about Taylor series. Okay. So, Taylor series is something else that's really awesome, right? So what you do is you go, hey, polynomials are a vector space. So what I'm going to do is I'm going to get the infinite polynomials, and they're going to be a vector space too, with a basis which is the ordinary polynomials. And then you say, David, what the hell are you talking about? That's algebra again. So you see, it's so cool because it's all really algebra. It's not calculus at all. Sorry. You can tell that I've had a long day in the Maths Learning Centre. I'm really quite off the wall today. So Taylor series is a way of representing any function as sort of an infinite polynomial. Okay? So my goal is to get any function and write it as something plus something x plus something x squared plus forever. If I'm really lucky, my function will already be a polynomial and I'll be able to stop at some point, but hopefully I'll go on forever. And it might be that instead of x, I might represent it like this. And instead of x, I'll have x minus a. No, I haven't put an x minus a here because my aim is that this all expands out to give f of x. Okay, so that's the whole idea of Taylor series. So a series in maths is anything that's added together, and that's why it's added together. And you normally write them as an infinite sum with a sum sign, right? And this A here is called the centre. Right, so there are ways of finding Taylor series by using derivatives, and there's a whole sort of magic about how factorials behave near derivatives that allows you to figure out what that an is. Okay, but the whole idea is that you're just supposed to figure out some numbers that go in that spot, and hopefully there's a formula based on n that tells you what that is. You know, that's your goal. You want a formula that goes in there that tells you what the an is. Okay, so what you need to be able to do to succeed in this course is to know some Taylor series without having to calculate them. You just have to know. Right? So there are at least 4 that you should just know. So e to the x or z works in complex numbers too is the sum from n to equals 0 to infinity of x to the n over n factorial. That is e to the x for any value of x, including complex number x's. Okay? So that an I'm referring to is 1 over x to the n. No, 1 over n factorial. So just so that you know, that's like 1 plus x over 1 plus x over 2 squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus blah, blah, blah. Okay, that's what this means here. So the factorial, in case you've forgotten, is 1 times 2 times 3 times 4 up to n. except 0 factorial, which is just 1, to make it all work in the formula. Okay, e to the x is equal to that. You just need to just know that. And 1 over 1 minus x is that. So there's nothing attached to them, it's just 1 plus x squared plus and so on. And this only works if the absolute value of x is less than 1. Or if it's a complex number, the modulus of x is less than 1. Okay, so they're your two most famous Taylor polynomials. These are in fact Maclaurin polynomials technically, because a Maclaurin one has that a, that centre is 0. And then there are two more that based on your Maple TA assignment this week, your lecturer apparently expects you to know. So I'm going to write them down too. Sin x. So sin x looks extremely similar to e to the x, but because sine is an odd function, it only has the odd powers. Okay? And also, it flips back and forth between plus and minus. Okay, so that's what it looks like without writing it as an infinite sum. That's the Maclaurin series for sine. It looks like the one for e to the x, but it's only got the odd powers, and it flips back and forth between plus and minus. So it starts at the first odd power with x, and it starts with plus, and then it goes back and forth between plus and minus. Okay? I help myself to remember this one because if I divide everything by x, I'll get sin x over x equals 1 plus stuff. And if I sub 0 into that, I'll get 1. Sin x over x is 1 when x is 0. So that helps me remember that. But also, it's an odd sine is an odd function, so it only has odd powers. And as an infinite series, you only want x to have odd powers, so you put a 2n plus 1. And it flips back and forth between plus and minus 1. And so this doesn't have a 2n plus 1 in it, because otherwise it would always be minus 1, it's just an n. So that's sin x. And cos x is similar, but being even, cos x has the even powers. So we have 1 and x squared on 2 factorial, and x to the 4 on 4 factorial, and x to the 6 on 6 factorial, and it will flip back and forth between plus and minus. Same as the way sine does. And so as an infinite series with a sum sign, it's only got the even powers, and it's got its minus 1 to the n as well. You can just check if you've got your minus 1 to the something right, is if when you put in 0, it gives me a plus 1, which matches with my first power. And if I put in 0, I get 2 times 0 plus 1, which is x to the 1, which is the first power. So, yeah. So, based on your Maple TA, your lecturer expects you to remember that. So, just thought I'd put it in there. Okay, they're technically Maclaurin series, because they don't have an x minus a, it's just x. But the key to them is that because Maclaurin series exist, for most functions, and any function that has a Maclaurin series has one forever. I'm just looking up something in my... it means that you can find Maclaurin series and Taylor series for other stuff by just being a little bit fancy. So I can, for example, find, just as an example, find Find the Taylor series for 1 over 1 minus x centred at 3, for example. So I've got a Taylor series centred at 0. Which is what that one is, because it doesn't have an x minus a. And I need to rewrite it so it's got an x minus 3 in it instead of just an x. That's really very easy in inverted commas to do. If I just need to rewrite this one to look like this, but with an x minus 3. I really hope this works. Just give me a second. So I'd really prefer that x to be an x minus 3, but I can't just go putting a minus 3, so I'll just do that. So my x I've replaced with x minus 3 plus 3. And the reason I've done that is so that I can get an x minus 3 in there without changing what it's equal to. So I've just added 0 creatively. And then I'll expand that out. So 1 minus 3 is minus 2. So I'm way closer now, because I've got a 1 over something minus x minus 3, but this is supposed to be a 1. So I'm just going to divide the top and bottom by minus 2. Oh, this is going to be worlds of pain. It's looking pretty good. Okay, cool bananas. And I just need a minus. So now it's one more step. I don't know if this is necessary, but I just thought I'd show you. Now, oh no, there's a minus in here too. Now that part there, 1 over 1 minus something, I know what the Taylor series is for that, so I can just sub it in. Ta-da! Done. So that thing there is my x, which I sub into the original. And if I'm really clever, I should probably expand it out and do something like minus 1 to the n over 2 to the n, x minus 3 to the n. Magic! Okay, most of the things I saw in your Maple TA assignment were not like that. They were more like, you know, find the Taylor series for sine of x minus a, which is like way easier because you just go like, all right, you know, sine x is this. It's the odd ones, right? But I don't want x, I want x minus a. Cool, I'll just sub in x minus a. And that's it. It's great. The reason that works is that if a function has a Taylor series, it's only got one. So if I find an infinite series which has the right x minus a in it, and it does, and if I find any infinite series that works, it must be the only one. So it's awesome. Okay, that's revision of stuff from last year. But except one more thing, if you actually want to find out what those coefficients are, you can do it by using derivatives. So when you write this, if you have something like that, just, you know, for general functions, then that an is found by differentiating this. So the an is the nth derivative of x at the point A divided by n factorial, which is looking remarkably similar to what you did in Maths 1B. So the easiest way to actually do that, if you ever are called to do so, but I'm pretty sure in your notes you said that's not what we're aiming for here, is to actually take the original function and start differentiating it, and then start subbing in the point at which you want the centre to be. But what we're supposed to do, now that we are older and wiser, what we're supposed to do is avoid doing that at all costs and do that stuff, like with the fiddling and chucking in x minus a's instead of x's, and that'll work much better. And I'll do a proper example, like from a past exam or something at some point, so that you can see how that works with complex numbers. But I needed to just remind you, and I'd like to put it here because it's of the flavour of Maths 1B, so it's good to have it first for future students. Right. I'm pretty sure my pages are still numbered consecutively. As long as they're strictly increasing, it'll be okay. Okay. Right. Now onto the complex calculus. So, as far as I can tell, there are two extremely important things to remember about actual complex calculus. One is that it works the same as ordinary calculus, pretty much. So that's really the most important thing to remember, other than all this stuff on the Laurent series. So first let's talk about derivatives. Derivatives. Same as for real numbers. That's pretty much it. Okay. I know there's a proper definition of when things are differentiable, and we can deal with that. But it's pretty much the actual derivatives themselves, when you get to the point of actually calculating them, are the same as for real numbers. Okay? So, that's lovely. And there are particular rules for telling if a function is differentiable, and they are based on your real number functions. But same as what you've always used to, ln does what ln does, everything does what it does. So, you know, the derivative of e to the z is e to the z. And the chain rule still works. You know, the derivative of e to the iz, well, it will be e to the iz, and because of the chain rule, it'll be the derivative of that, which is I, because that's the constant that's next to I. And that's just it. You know, it's not really more special than that. And sine and cos still do what sine and cos do. Shine and cosh still do what shine and cosh do. ln does what ln does. It's just... ln you have to be a bit special about because it's a bit crazy. Because e to the power of something, there's multiple things that give the same answer. ln has some strange behaviour. But as long as you only use the principal argument, you'll be good. Yep. So, just making sure I'm not you know. Okay. Just give me a second. Really? Oh, no. You'd be familiar with David's general procedure of making it up as he goes along, and it sometimes means he has to stop and just have a quick check that he hasn't missed anything yet. Okay, so there is just one little quirk that you need to remember as far as I can tell, which is how do you tell if a function is differentiable, a complex function is differentiable. So if your function is defined using the x and y, like, you know, function of x plus y, I y, there's a particular way of telling if it's differentiable. So if f of x plus I y is defined as u plus iv, where u and v are functions of x and y, okay, they're functions of x and y, then you tell if it's differentiable by using the Cauchy-Riemann equations. Riemann? Cauchy-Riemann? Cauchy-Riemann, yes, okay. One of the problems with reading things that you've never heard pronounced aloud is you sometimes do them wrong. It's like Ori. Don't know if you've ever... You know Ori? Oh, you think that's pronounced awry. Oh, no, Ori. Sorry. Anyway. So the idea is that you're supposed to differentiate them, each one with respect to the other, and if this certain equation works out, then it's differentiable. So if you do du on dx, it shall come out to the same answer as dv on dy, and du on dy will be minus the answer for dv on dx. And then it'll be differentiable. But remember, everything I said higher up the page doesn't technically define your function in terms of the x and y. It just uses the z raw as a whole, right? So this Cauchy-Riemann thing only really applies to things that are defined as x, y. If you're asked ever to show that e to the x, e to the z, for example, is differentiable, then you'll have to redefine it in terms of x and y. Not that I have no idea what your lecturer is going to do in the exam. I wouldn't be surprised if it was very similar to last year's exam, because lecturers, when they take a course for the first time, don't like to change things too much. Unless they're like, I don't know. No, I really shouldn't say his name anyway, so... certain professor whose name rhymes with Bony Bobbits. Anyway. Okay. So that's how to tell if something's differentiable. If it's defined in terms of x and y, just some random function. Everything else, is fine. Okay. Everything else you just define straight with z using functions that you're familiar with. And that's differentiation. Integration. Integrals are awesome because they behave almost always the same as integrals for ordinary real numbers. And the best way to do this is to define it by example. Okay. So here's the thing. When you had real numbers, right? When you had real numbers, you had your x-axis, and then there was a function on the y-axis, and the function told you how high the y goes for every x. And then when you did an integral, you did a little bit of a zone here, and the dx changed a bit, and then the dy, the y. The height went up and down a bit, and you just added up all those little heights times dx. Ta-da, that's the integral. Okay? Problem is, with complex numbers, with real numbers, there's only one place on the real number line where you can actually draw. There's only one place on the real number line where you can draw a path, right? It goes from here to here. But if you're in the complex plane, that's not so easy. In the complex plane, you could draw like, all sorts of fun stuff. And, right, it's great. So now we can do an integral across this path, and we can go, well, do a little bit of path, and then there's some sort of height, which isn't really a height, because it's actually a complex number. Okay, and so instead of being just an x, it's an x. Instead of just being a y, it's an x and a y, and it's supposed to add them all up. And oh my goodness, it just gets into worlds of pain. Okay, but the theory says that if there are no discontinuities enclosed within the path, then it doesn't matter. You just do it the way you always do. Okay? So if I said integral of some function, right, let's just do a classic function like e to the z, along this path, right, that path there. Well, and so you do like, which is called c. So we'll go like the integral across c of e to the z dz. It's great. Do you know what? Since e to the z doesn't have any discontinuities, I can just do this. And integrate it as if it was an ordinary real function. And that's it. It's great. There is absolutely, and this is because, since e to z is analytic, analytic meaning differentiable and integral. So it doesn't have any discontinuities inside any of the loops of the curve, and so therefore the integral is path independent. I could use any path that I like between a plus bi and c plus di, and it would always give the same answer for the integral. This is the magic of complex integration. Okay? We didn't notice that this was happening when we did real integration because there was only one path that we could possibly draw. It went from here to here, right? But when we were doing complex numbers, there are any number of paths that go from here to here, but it still doesn't matter because complex numbers are awesome. Okay? So that's it. Okay, there is nothing more than that. Presumably you could simplify that and get it down to a single complex number if you wanted, but who cares? So, and also there's a thing, it's classic in an assignment or an exam question for one of those points to be 0, and e to the 0 is 1. So you can figure out what some of these things are. Okay. So that's great. But this will only work, only works. It only works if there's no discontinuities inside any loops. Okay, e to the z doesn't have any discontinuities at all, so we're all good. But a function that does have discontinuities inside one of the loops, if it doesn't form a loop, doesn't matter, okay? But if it forms any loops and there is a discontinuity inside the loop, then something else happens. Okay. So then we get down to this thing of what if there's a loop? Okay? And it depends on what kind of discontinuity it is. So in Maths 1B, there are only two kinds of discontinuity. There was your essential and your removable. But in Eng Maths 2B, there are multiple different kinds of discontinuities, and they are called poles of different order. So instead of discontinuities, we will call those poles. Okay, so supposedly you're supposed to do a path integral, and you're supposed to do like a parameterization of the curve, but it's not actually necessary unless your function has this horrifying discontinuity, that the path. If there's a discontinuity on the path itself, then you're stuffed. But as far as I'm aware, at least last year, anything that did that wasn't examinable. So it's probably still true this year. Okay. All right. So here we go. If there is a pole inside your zone, okay? If there's a pole inside your zone, then there's a rule for telling what to do. And here it goes. And I'm just going to summarize this, and I'm just going to try and remember it and skip to the straight deal. So f of z will have things that make it discontinuous, and in general they are seeing a 1 over z minus something. That's the problem. Okay? This is my general form. It's g of z, some function g, and it's got x minus a to the m, z minus a to the m, z minus b to the n, and blah, blah, blah. Okay? So the idea is that you'll see something like that. I'll give a proper example in a minute. This power m is more or less the order of the pole. I'm sure there's a proper definition, but that works. Okay? So that is a pole, that point A is a pole of order m, where m is whatever power is in that spot. Okay? And depending on the order of the pole, and g of z doesn't have any of this stuff. Okay? And depending on the order of the pole, it will change slightly what you do, because it will be involved with the derivatives. So what we're going to do is that we're going to say my pole of order m, which is the one that has m here, okay, I'm going to find the part of the function that doesn't involve the z minus a. Okay, in essence, I'm going to multiply my function by z minus a to the m. Okay? G to z over other crap not involving a. And that's a new function, which I'm going to differentiate some number of times, m minus 1 times, and then I'll do something with that. So this is the first step. I'm just going to call this h because I've already used g. And then I'm going to go the m minus 1th derivative of h, which will be something. And then I do the limit as z goes to a of that. And this will now be a complex number. And that complex number is the residue. And then the integral, okay, the integral around any path, closed path, that contains the point A will be that times 2 pi I. Let me just check that I've got that right. Oh, on n factorial. Sorry. Let me just check something. Oh, this isn't quite the residue. Sorry. Just give me a second. Sorry. We're going to sub in A, and we're going to divide by, that's a minus. Okay, I'm going to fix that in a second with an example. Right, that's the residue. And then any integral around any path for path C containing the point A is 2 pi I times this residue. Okay, and I know that's pretty fanciful, but an example will make it make more sense. Okay, so let's see. Z squared plus 1 over Z minus 1. Oh no, just a second. Z squared plus 2 over Z minus 1, Z minus I squared. The reason I changed that top is so that the thing on the bottom doesn't cancel with some of the top. Okay, that function has two poles. It has a pole at 1 and a pole at I. And those two poles have different orders. The order of the pole at 1 is 1, and the order of the pole at I is 2. And I can figure out the residues of those directly by using this particular rule. Pardon me. So the residue... No, let's write my working different. The pole at Z equals 1. Okay, which is an order 1. So this order 1 pole, I remove the bit that involves a Z minus 1. I'm going to call that G. That's great. And then I differentiate it m minus 1 times. So I will differentiate it no times, because m minus 1 is 0. So differentiate 0 times. Okay? And then I will do the limit as g goes to 1. Limit as, Z goes to 1, so g of z is 1 squared plus 2 over 1 minus I squared, which is not happy. I should probably do some maths to try and figure out what that number is, but I'm not. Well, maybe I will. So 1 squared minus 2 times 1 times I plus I squared. Oh, cool, turned out nice. So let me just see if I've got that right. 1 squared minus 2 times 1 times I plus I squared, and I squared is minus 1. And that is great stuff. If I times the top and bottom by I'll get 3 on 2I. Nice when something works out, even though you didn't plan it. So that's the limit. And then I just need to divide it by m minus 1 factorial. So the residue at z equals 1 of f of z is 3 on 2i divided by 0 factorial, which is 3 on 2i, which means that the integral around anything that contains that pole, as long as it contains only that pole, will be 2 pi I times that, which will be 3 pi. That's great. Minus 3 pi. The pole at z equals I, on the other hand, is order 2. So I remove the bit that actually involves the z minus I. Okay, I remove the part that involves z minus I, which is tantamount to multiplying by z minus I to the m. And m minus 1 is 1. So differentiate 1 time. So g dash z is quotient rule. So differentiate the top, keep the bottom, keep the top, differentiate the bottom. Two z squared minus 2z minus z squared minus 2. Okay. And then I do the limit as z goes to I of g dash z, which is I squared minus 2i minus 2 over I minus 1 squared. Minus 2i minus 3. Now 1 minus I squared was minus 2i, so this will be minus 2i as well. I can get rid of all those minuses, I suppose. Two I minus divided by 2i is 1. 3 divided by 2i, we already did that. Okay, that's what it comes out to apparently. Times top and bottom by I get minus 2 minus plus 3i. Yep, okay. And so finally the residue, so the residue at z equals I of f of z is this number divided by 1 factorial, because m was 2. Yep. Which is 1 minus 3 on 2i. Okay, so that's finding residues. If I wanted to find the integral of this along some sort of path, I'm not going to do that because I don't like the concept of... No, I can do that. Okay, so if I wanted to do the integral of this around a curve, and I will draw my curve. Right? My curve there. I think it's supposed to go anticlockwise. Alright, that closed curve encloses both the I and the 1, so I'll just have to add together the residues. So 2 pi I times the sum of the residues, so the residues were 3 on 2i and 1 minus 3 on 2i, which is 2 pi I times 1, which is 2 pi I.
David, you may need to change the arrow or make that minus.
Really? I can't remember which way it goes.
It's N.
Oh, did I? Oh, yeah. Apparently if you go the other way, it's minus, which would make sense. So yeah, just for those who couldn't hear, the audience, I said anti-clockwise and then I drew it clockwise. So I was just looking from the other side of the clock. Which of course will change the answer. But since I can't tell my left from my right anyway, it's completely understandable. People used to tell me to tell my left from my right, I had to make my hand make an L. I'm going, which way do you put your hand? For that matter, which way does an L go? Yeah, so it wasn't particularly helpful for me. All right. The only thing I would say is that it loops around something twice, you have to include the residue twice. So if it went round like that, then it would actually be going around the one twice, and so you have to include that twice. That was in one of the written assignments once. Okay, now that's great, that's lovely, but there is another way to find residues. Okay? Because what if your function is not something that you care to differentiate several times? Okay? So instead of differentiating it several times, there is another way to find the residue. Okay? So our second way of finding the residue is using Laurent series. The key thing to remember here is that we're not just doing Laurent series for no good reason. It's all in the service of trying to find integrals. Okay. So as far as I can tell, and I'm sure there's some really fancy stuff that is better terminology than this, a Laurent series is like a Taylor series, but you're allowed to have negative powers. And if the negative powers don't go on forever, then it's pretty good because you'll be able to do great stuff like what we did just then. You'll be able to find integrals and possibly even derivatives at most useful places. So as long as your negative part doesn't go on forever, that'll be great. And the thing that you're most interested in is the one that goes with the negative 1 power. And as far as I can tell, the main deal with the Laurent series is that what we really do is we calculate our Laurent series by first finding a Taylor series. Alright? So first we find a Taylor series, and then we sub in the thing that we're looking for, and that gives us the Laurent series, and then we're great. So there's two things to just, it's best to do by example. So let's look at this function. Sine of 1 over z minus 4. Okay, so sine of anything, as long as that thing is defined, sine of anything is an awesome function, and it's defined everywhere, and its integrals work and its derivatives work. The only issue we're going to have is that when z is 4, this function doesn't exist. That's okay, because the whole point of this is to figure out precisely what to do about the fact of what happens when z is 4. So if z wasn't 4 and I wanted to differentiate this, I'd just differentiate it. You know, I'd use the chain rule or something. Okay? And if z wasn't 4 and I wanted to integrate it along some path that didn't go around the pole of 4, it'd be great. Wouldn't care. This thing, if I did a little loop that doesn't include 4, the integral would be 0. It doesn't include the pole. Okay? So, I'm pretty sure. So, the issue is, what do I do when z is minus 4? Well, that's fine, because I just use Taylor series. Sine of z, would be, let's see, it's the same as e, so it's x to the something over something factorial, and it's only the odd ones because it's an odd function, and it flips between plus and minus 1. So that is the Maclaurin series for sine. In fact, I should write that. Taylor series for sine z centered at 0, possibly Maclaurin series. And then I just sub in 1 over z minus 4. It's awesome. Right, and that'll totally work at every z other than 4, because Taylor series just work that way. You sub in whatever you want, and it'll still work. And then I just do some algebra, and I'll get something pretty nice. So that z minus 4 is z minus 4 to the minus 1. And then, I guess, and that's pretty much it, right? Great. I could possibly put the z minus 4 on the bottom and make it 2n plus 1. Doesn't really matter. Depending on what Maple TIA is asking me to do with this. So, there you go. And that is a Laurent series for sine of 1 over z minus 4. That's great. So if I wanted the residue, just to be clear, the residue of f of z at z equals 4 would be the coefficient that gives me the 1 over z minus 4. Okay? Coefficient. That's what it is. And that would happen when n is 0. So it will be, let's see, minus 1 to the 0, 2 times 0 plus 1 to the factorial, which is 1. Yay! That's the residue. Because when n is 0, I get z minus 4 to 1. Magic, right? So just as a separate example, what's that? Where here? I subbed in n equals 0 into this. Oh good, I was just checking it was recording. I had this horrifying fear every so often that I forgot to press record. Okay, so you've got to look to say what does n have to be in order to make this power on the z minus 4 equal to 1 on the bottom. It is totally the minus 1 power. No. Boy. Okay, e to the z over z minus pi I squared. That'll work nice, I reckon. So let me attempt to integrate this. That's my pi I. Okay. So I'm going to integrate this function. What? Oh, crap. Thank you. Around that curve, which encloses pi I, which conveniently happens to be that number. So I'm going to do it via Laurent series. Okay? Ah, crap. They're all in Z's now. Okay, so that's my Taylor series for e to the z. It's z to the n over n factorial. I'm actually going to need to have one centered at pi I. Technically, I don't need to do this with Laurent series. It would have actually been easier just to do the residue the ordinary way, using derivatives. But I'll do it the other way as well. So just a second. This is the using... I'm just trying to illustrate how the Laurent series thing works. So I've got a Taylor series at 0. I need it centered at pi I. So e to the z is e to the z minus pi I plus pi I, which is e to the z minus pi I times e to the pi I, because of course plus up in the powers is times down below. So in this first step, I've arranged for there to be a z minus pi I by subtracting pi I and adding pi I up in the powers. And then I want the z minus pi I by itself, so I've just done this. And e to the pi I happens to be minus 1. Which is why I chose e to the pi I anyway. Okay. And then, of course, I sub, so without the minus, this is the same as up here, but with a z minus pi inside of a z. So I sub the z minus pi into there, and that is my thing. So to be fair, we should do this. Okay? And now what I really want is the one for z minus, for that function divided by z minus pi I, because that was my original function. See, it's got z minus pi I squared, actually. So e to the z over z minus pi I squared will divide all of this by z minus pi I squared. So all my powers are going to go down by 2 because I divided by z minus pi I squared. So the residue of f of z as z equals pi I will be the coefficient of z minus pi I to the minus 1, which will happen when n is 1. Okay, so I need this to be z minus pi I to the power of minus 1. I need that coefficient. So coefficient of z minus pi I to the minus 1, or if you like 1 over z minus pi I, which happens when n equals 1. So i.e. n equals 1. So we get minus 1 over 1 factorial, which is minus 1. Yep. So remember that you're not including the part that involves the z minus pi I, it's everything else, all the coefficient part, not that bit. The integral around that curve will be 2 pi I times the residue, which is minus 1. Please correct me if I'm wrong, but I'm pretty sure that's how it works. That would be using residues to do this. The reason I chose that example was so that you could see that sometimes the Laurent series happens by subbing something in raw, like the 1 over z plus 4. Sometimes the Laurent series happens by creating a Taylor series first and then dividing it by something. Okay, I just want to show you that I could have done that via derivatives. Okay, using, now there's a word for that. Not Cauchy's inequality. Okay, so I could have used the formula in, yep.
To use the Laurent series, does it have to be centered at your pole? Like, is that?
Yeah, so to use the Laurent series, the question is, to use the Laurent series, does it have to be centered at your pole? Yes, to use the Laurent series for a residue at a pole, yeah. To use the Laurent series for the residue at a pole, it has to be centered at your pole. So that's why I had to do what I just did. I had to convert this one to be centered at pi I. But plus, if I hadn't done that, when I divided it by the z minus pi I squared, I would have gotten z divided by z minus pi I squared, which wouldn't have told me anything useful. Okay, so you have to make the top match the bottom. Yeah. There's an even crazier thing you could do with this one. But okay, so I can use the formula instead. This is using the formula for the residue instead. So I could have said, all right, I've got a pole z equals pi I of order 2. Okay. And then I need to figure out the part that doesn't involve the pole, which is just e to the z. Then I need to do, m minus 1 is 1, so differentiate 1 time. So g dash z is still e to the z. And then I do the limit as z goes to my pole of g dash z, which is e to the pi I, which is minus 1. And then the residue of my function at z equals pi I is that number I just found divided by the m minus 1 factorial, which is minus 1, which is exactly what I got last time. Okay, so I mean, if your lecturer tells you you must do it using Laurent series, then do it using Laurent series. If they don't tell you how to do it, look first to see if you can use the derivative sort of formula to find the residue first. Alright, so I have mod that clock be an hour different. I've got about 20 minutes during which you can ask sort of anything, and I will do my best. So ask away. Sorry? Which part of the course was that from?
Like right at the end, like the last slide.
Okay, let's have a look at that. Never heard of it, but we'll give it a go. Just calm down a bit, because someone's asked me about Jordan's lemma, which, being on the last slide and therefore probably not in the Maple TA assignment, is something I don't know yet. So give me a second. So Jordan's lemma says improper integrals. I'm going to read what she said. Improper integrals. Right. Improper integrals involving twigs functions can also be evaluated using the residue theorem. For this we need Jordan's lemma. For the part C, which is capital R e to the I theta, which is a semicircle of radius r centered at the origin, okay, let I be equal to the integral of e to the I m z f of z dz, where m is a positive real value. F of z is a meromorphic in the upper half plane. M is a positive real value. Okay. If the limit as r goes to infinity of f of r e to the I theta is 0, then I goes to 0 as r goes to infinity. Okay. How about I try that example as a way of trying to figure out what this means. So you can now see how David deals with something and how you might deal with something that the lecturer has said but doesn't seem to mean anything. I think the idea is that you can do real integrals by just imagining them as path integrals. Yeah, so let's see. Just let me look back a bit. Have you got... the person I borrowed this from I think has left. He better come back for it at some point. I'm making this up, as you well know, by my humming and hurrying. I'm just trying to figure out how you do this thing with the infinite integrals for a start. So, okay. So, Someone's got an idea? No? This is from the last slide of the lecture notes. Well, Jordan's lemma says well, cos x, okay. Jordan's lemma concerns a function like this, e to the I m z f of z dz, where m is a positive real value. I know that cos can be written in terms of those things. Okay? So my guess is that I should rewrite cos x in terms of e to the something. The 1 over 1 plus x squared dx, if I sub in r e to the I theta, no idea. Has someone got the example?
Yeah. My writing is very messy.
Can't be worse than mine.
Starts there.
That's not worse than mine.
I think what they said was that cosine of x is the real part of e to the I theta.
Yeah.
Oh, yeah?
And then from there, I don't actually know where we go from there.
Okay, so let's try and decipher what this thing says. So, first it says we sub in, so we consider curve C like that, where this is minus r and this is plus r. Yep.
And the curve back from minus r to r.
Yeah, it must be the same if it doesn't go through a pole. Yep. So this bit here is that integral if r goes to infinity. Yep.
I think you have to close to the curve or something. So close the curve from minus r to r along the real axis.
Yep.
And that's just second.
I'm just having a look through this example here, just to try and pull out what we're supposed to do with this. Okay, so first we're going to have a look at the 1 over 1 plus x squared. Okay. This is our curve, comes around this way. Made of two curves, a bit that's along the axis and this bit over here. Aha, I think we're doing well here. Okay. Yep. Okay, so we can do this. We can go the integral around this curve of f of z dz is the integral from minus r to r of f of z dz plus the integral around the half circle. Yeah? But being a closed loop, it will also just be 2 pi I times whatever the residue is. Yep? And that's the idea of how we calculate this. Cool. Yep?
Made a little bit of sense, but I didn't know.
Yeah.
Not really.
Okay, so we're saying we're not going to go to infinity, we're just going to go this far, and then we're going to do the limit as r goes to infinity.
Yeah.
And we know that if we just go this far, this loop, its integral will either be 0 if there's no poles inside the loop, or it'll be 2 pi I times something. And then this loop can be made of this bit, which is the bit we're actually looking for, and this bit. And there's a theorem that says what this bit is. That's what Jordan's lemma does. Jordan's lemma tells you what this part is. Okay.
2 pi
Cool.
minus the sum of the
No. Yeah. Cauchy's integral formula tells you what the whole loop is. Jordan's lemma tells you what just that bit is. Okay, cool. Just making sure. So around the half circle, that's what Jordan's lemma's for. And that's where I'm going now. So around the half circle, z equals r e to the I theta. And theta is between 0 and pi. Okay, because the radius is r, and r e to the I theta, but we're only using the top half, so it's this. So that's what the half circle is. Okay, so on the half circle we have that, and Jordan's lemma was specifically referring to the r e to the I theta. Okay. Oh wow. Sure. Ugh. And then we're supposed to sub in the r e to the I theta. Right. So we're actually going to figure out that curve. Yes?
Shouldn't theta be from pi to minus pi?
We've got someone saying, shouldn't theta be from pi to minus pi? That would give you a whole circle. We only want this half. From pi to minus pi to pi would be all of that, but we only want this top half from 0 to pi. Good point though. And then because we can't use because there's weird crap going on, we have to figure out this one using methods of subbing in. Okay, so the integral around my half circle, I'm not going to do the bit involving the cos. Yep, not going to do the bit involving the cos, just the other bit. Okay, that bit there. And the thing is that dz will be related to d theta according to this. So actually this is telling us to do a substitution. So I ignore the cos because it's writable as e to the I something, plus or minus e to the I something. So I ignored the cos. I figure out what this integral is by doing this substitution. Okay, so dz on d theta is I r e to the I theta. So dz is I r e to the I theta d theta. And I get from 0 to pi that. Great job. Which has this fun integral, which I have no idea.
That's the bit where I got lost.
Right, but apparently you have to figure this out this way. Oh no, just a second, we only want the length of this. Okay, it's looking better. So if you have a look here, Jordan's lemma refers to the length of that. It has a length here. Cool. Okay, so let's just go back a bit. We draw our curve. We focus specifically on the half circle to begin with. And on the half circle, we ignore anything involving cos and sine. And we do this substitution. And apparently, we can bring the length inside the integral sign. Not entirely sure why, but I'm all good with that.
We can't see.
Oh, sorry. Plus whatever crap is on the bottom there. Now I should expand it out. 1 plus I squared is minus 1. Oh, look at that. Wow. Okay. R squared e to the... Where'd that 4 come from? I'm sorry. I have no idea. I'm really trying. But if I'd known yesterday, I might have been able to figure it out.
My notes probably aren't helping either. They are.
That's okay. Your notes is what you have to work with. This is my job. Help people to figure out maths with what they have to work with. Unfortunately, I'm not doing a good job of that at the moment. I'm sorry, some stuff is just... There's a 4 that I don't understand where it came from. I think somehow you're supposed to do this bit and it's supposed to come out that you get an answer that as r goes to infinity, this goes to 0.
I think it's something similar in the exam 2011.
What's that?
Isn't it? Something similar in the exam 2011. maybe?
2011?
Yeah. The solution to...
Have you got the questions?
Well, I'm not here, but it's on my unit.
Oh, I can't access your MyUni. Well, hopefully, between now and Friday, we figure it out. If I do come up with something, I'll record it and put it on my website and let you know. But I just can't do it right now. That example's not making any sense. So, yes.
What was the original equation? Was it 1 over 1 plus x squared or 1 plus x to the 4?
Well, the original question has 1 over 1 plus x squared.
Yeah.
But in the example in the lecture notes, she keeps going on about 1 over 1 plus x to the 4.
I think maybe in the example, she did 1 over 1 plus x to the 4 and 1 over 1 plus x squared.
Okay.
Just check that equation at the start of that example.
Oh, she did, and I don't know if there's a good reason why, or if she just
stuffed it.
Okay, we'll run down this road.
Yeah, continue with that.
I'll continue with this one, make a new one. So we get 2i theta. Okay. Cool, because we squared that. Which is integrable. Okay.
I remember we subbed in something like where we're doing a length, subbed in when constants,
Just working my way through it. So lengths can be brought in over plus and minus and times and divide. Not plus, they can be brought in over times and divide. The length of I is 1. The length of r is r. The length of e to the I theta is 1. So when I do that length, I get r on the top. That's where that comes from. Okay, so the length of I is 1. The length of e to the I theta is 1, so I get r. And then on the bottom I've got the length of 1 minus r squared z to the 2i theta. Sorry?
Isn't z is an e?
Oh crap, it is totally. Thank you. Where'd my z? Oh, that's all theta now. Okay. And presumably I can figure out the length of that. So 1 minus r squared e to the 2i theta is a complex number. Let me just think about where that complex number is to try and figure out how long it is. E to the 2i theta would be wherever it is. That'll be 2 theta. And it'll be r squared this way. And then we do minus that, which would be over here. And then we add 1. That's not at all helpful. She's done this thing here. Oh, duh! The length of something is times by its conjugate. Right. Doing so well. We're nearly there. Where have we been? We subbed this substitution in, we got to here, we brought the length inside, we dealt with the lengths as far as we could, and then we have to figure out the length of this. But this should be this times its conjugate. So the conjugate of 1 is 1. The conjugate can be brought inside any subtractions and timeses. So this will just be minus 2i theta. Because conjugating the 1 is 1, conjugating the r squared is still r squared, because it's real. Conjugating the e to the something is putting it as a minus power, and I can expand that out. So 1 minus r squared e to the 2i theta. Sorry, minus 2i theta minus r squared e to the 2i theta plus r to the 4. Yep, because e to the minus I theta and e to the plus I theta cancel each other out. Lovely. Doing so well. And then e to the minus 2i theta and e to the plus 2i theta are conjugates, so they cancel each other out. So I get 1 plus r to the 4. Yay. Okay. This is so good. And so therefore, my integral of my half circle of f of z dz is the integral from 0 to pi of r on 1 plus r to the 4 d theta.
Do they really cancel out? Like, how would they cancel out there? Wouldn't it have the real part of those?
Oh, it totally would have the real part. What's the real part of that? Cos. Oh, crap. Just a second. 1 minus r squared e to the minus 2i theta plus e to the 2i theta plus r to the 4. And the conjugates multiplied would totally be the length, wouldn't they? But that's okay. It's all good. Okay. All good. Okay, so that would be cos of that minus sine of I sine of that. Cos of, okay, so that would be because this is cos of 2 theta plus I sine of 2 theta. This is cos of 2 theta minus I sine of 2 theta. So the sine theta bits will cancel, so I'm going to get 2 lots of the cos of 2 theta, which is not pretty. But that's what I've got. And then so that's where she's up to this thing here. And then she said that's less than her, okay, why not? Don't know why she's doing that. Wouldn't it have to be greater than? Oh, gosh. This is just painful. Alright, I think I may have done my dash. I'm sorry. I can see what she's doing now. She's saying, well, whatever this length is, it has to be less than or equal to something. And because it's less than or equal to something, and that something goes to 0, that limit goes to 0. So, whatever this limit is, right? It's cos 2 theta is less than or equal to 1. Yeah? So it's less than or equal to 1. So minus 2 cos 2 theta is greater than or equal to minus 2. I'm just building this up. And so therefore minus 2r squared cos 2 theta is greater than or equal to minus 2r squared. And so therefore 1 minus r squared 2 cos 2 theta plus r to the 4 must be greater than or equal to 1 minus 2r squared plus r to the 4. Okay? Which happens to be 1 minus r squared squared. If you factorise it out. And then therefore 1 over this must be less than or equal to 1 over 1 minus r squared squared, and that's r. Yep. So therefore, that length, therefore the integral of that thing must be less than or equal to the integral of this. That. And a less than or equal to is a good plan because the whole point is to show that it goes to 0. So if I can show it's less than something that goes to 0, then that'll work. Okay. And so when I do integrate that, I get r over 1 minus r squared times pi. And as r goes to infinity, that goes to 0. Because I've got roughly r to the 4 on the bottom and r on the top, so the power on the bottom is bigger than the power on the top, so it goes to 0. So this approaches 0 as r goes to infinity. Right. So we have therefore that the limit Why did we do all of that? We didn't bloody need any of that. I'm now going to achieve a Zen-like state. Say, this question in my exam is not worth the pain. I'm going to do the other questions in my exam. All right. Perhaps the moral here is that's a lot of hard work, and we don't want to have to go there. Okay? Because now we have, in the next lecture, so now that she's built you up and said, oh my goodness, my world has ended and my eyes are burning, now it says that all I need to do is find the length of that, and then I'll be good. I think. Okay. That was just crap. I think I've got it. We've now found the beginning. We have an integral of cos x over 1 plus x squared dx from minus infinity to infinity. And we're going to ignore the bit involving the cos. And sub in z. And then we're also going to sub in z equal re to the I theta. Okay, because that's what this says. It says find f of re to the I theta. where f is the bit that doesn't involve the e to the I something. Right. This is much better. So here we are, we've got this, okay? And so we've got f of r e to the I theta is 1 over 1 plus r e to the I theta squared, okay? Which is 1 over 1 plus r squared e to the I 2 theta. Okay? And then we're going to find the length of that. And that means that all I need to do is find the length of the bottom. Cool bananas. Just making sure I've got this right. I just want to do it properly. I think I stuffed that in right. Yep. Okay. Yes, I totally should. And this is the calculation I did earlier. Not sure where she's getting her 1 on r squared from. Sorry. But by the same reasoning I had before, this is going to work, right? Because this is greater than or equal to 1 plus 2r squared plus r to the 4, which is that. Because the cos 2 theta is greater than or equal to 1. Cos 2 theta is greater than or equal to minus 1. And so we're getting, therefore, the length of f of r e to the I theta is less than or equal to 1 over 1 minus r squared, which goes to 0 as r goes to infinity. Yes. So which... Okay. Cool. Because the r squared squared's got an r to the 4, and r to the 4 goes to infinity, and so 1 over that goes to 0. Cool bananas. And so therefore, based on this, that means that any integral, which is e to the I something, times f of z will go to 0 as r goes to 0. So the integral from minus infinity to infinity of e to the I x over 1 plus x squared dx no. Around the half circle. Okay? That's what Jordan's theorem says. Jordan's lemma says. You chuck in z equals r to the I theta into the but that doesn't involve cos, and you figure out the limit of the length of that as r goes to infinity, and it comes to 0. And it doesn't work unless it comes to 0. If it does come to 0, then Jordan's lemma says that the integral around the half circle comes to 0. Here. Okay? So Jordan's... Okay. That's what that says. So Jordan's lemma says, and that will be true of e to the minus ix as well, you know, doesn't matter which one. Okay, any power of any integer multiple of I will work. No, it won't. Does m have to be positive? Okay, just I. Okay. Cos x. So therefore, if we imagine our integral, it goes chunk like that. And we know that the integral around this top half, the half circle, the whole integral there is 0. So we have the integral around the whole curve, f of z dz will be 2 pi I times the residue thing, which I would figure out by figuring out residues with derivatives and stuff. The integral around the half circle. So this is when I've got e to the I x, by the way, is 0. And so therefore the integral here should be the whole integral minus the half circle. So it's the same as the whole integral. Because this bit plus that bit gives me 2 pi I times residue. Right. Okay.
Just skip.
Sorry?
I can say that the half circle integral is
What?
0. Could we just say that without showing?
The integral around the half circle.
Yeah.
That's because of Jordan's lemma.
Yeah, so we could just use that Kelvin on the exam. What do we have to show?
Well, no. All the other crap that I did is irrelevant. You do have to show this bit. To use Jordan's lemma, you have to show that the limit of this bit here as r goes to infinity is 0. Just the 1 over 1 plus x squared, the part that doesn't involve the cos. I'm still not quite there. If I knew about this already, I would have a much better explanation for you. This is currently this, right? It's not f of z, it's... Okay, and so therefore the integral from minus infinity to infinity. Oh, it's not that this half circle is z, it's the limit, right? The limit as r goes to infinity of that. And the limit... Fuck. Right, we know that the limit of the half circle as r goes to infinity is 0. That's what Jordan's lemma does. So we just do the limit of everything as it goes to 0, and this will be the same as the halves, as the whole circle times whatever the residue is. Because this doesn't depend on r. The whole point is the closed loop doesn't depend on the radius. Right. Okay. And then cos is e to the ix minus is the real part of this. So cos x is the real part of e to the ix. Yeah, that makes sense because it's cos x plus I sin x. And so therefore the integral of cos x over 1 plus x squared, and and dividing by 1 plus x squared, that's real anyway, so it's okay. Okay, so we've got the... And so the integral should work too. Right, so the integral from minus infinity to infinity of cos x over 1 plus x squared dx will be equal to the real part of this. Which is the real part of 2 pi I times whatever the residue was. Right. So, let's think this through. I think the steps that we took were, we had some sort of, something involving cos or sine. cos and or sine, right? And we had some sort of function here. Fuck. Anyway, I'm just going to talk it through. First step was to remove all the bits involving cos and sine. Yep. And the second step was to, with that part removed, sub in re to the I theta. And then we had to show show that that's less than or equal to something that goes to 0. Okay, so show less than or equal to something which goes to 0 as r goes to infinity. That was our goal. And then that would mean you'll be able to say, the next part of the working will say, therefore, f of r, show that the length of this. So the length of f e to the r I theta is goes to 0 as r goes to infinity, and therefore the integral of e to the I z f of z, right, from minus infinity to infinity is 0. That's Jordan's lemma. Okay, so after you've done this bit, you technically don't have to say this bit. You can just say, therefore, the integral with e to the I z times that function goes to 0. Okay, and then once you've said that, you can do your little split of the integral thing. Like that. And you can say the integral of the half circle of the original thing of the e to the I z f of it, of e to the I z I x f of x dx plus the integral from minus r to r of e to the I x f of x dx is the integral of the full curve e to the I x f of x dx, and that means that I can figure out this bit using residues. Okay, and I'm going to get that, and then it says that we do the limit. Now we do the limit as r goes to infinity, and the limit of this bit is 0, that bit there. And the limit of this bit is almost what we wanted. So we're going to get the limit integral from minus infinity to infinity of e to the I x f of x dx equals whatever the residue thing came out to be. Right, and then you do the real bit or the imaginary bit, and you get the bit with the sine or the cos. So then you can say, therefore, integral from minus infinity to infinity of cos x f of x dx will be the real part of whatever we got using our residues, and the integral from minus infinity to infinity of sine x f of x dx will be the imaginary part of whatever came out from our residues. That's how you use Jordan's lemma. That'll do. Cool. Well, I hope your exam is not that awful, and hopefully they'll give you a function that isn't so hard to do that limit on. All of that stuff I did earlier, I think that she just did a random example where she did an integral of something. But this one's easier. Okay, cool. Good luck on your exam, and yes, good luck studying between now and then.
Thank you.